The IEEE Historical Archives Center holds a wealth of information regarding the history of electrical engineering, the Nippon Electric Company known as NEC, and Nikola Tesla. Key areas of interest within the NEC collection include NEC history documents. These could include any documents, reports, or presentations that provide a detailed historical overview of the Nippon Electric Company, including its founding, key milestones, technological advancements, and global expansion. Also of interest are NEC annual reports, which are copies of historical NEC annual reports from different decades, particularly those providing insights into the company's financial performance, product innovations, and market share. Furthermore, NEC product catalogs, which are a historical catalog showcasing NEC product offerings over the years, including telephones, communication systems, computers, and other electronic devices, could be beneficial. Turning to the Tesla collection, there are several important categories. Firstly, Tesla interviews. These could be transcripts or recordings of interviews conducted with Nikola Tesla during his lifetime, providing first-hand accounts of his inventions, theories, and personal anecdotes. Secondly, Tesla research papers. These could include copies of Tesla's seminal research papers on electrical engineering, including his work on alternating current, polyphase systems, and wireless power transmission. Thirdly, Tesla correspondence. This includes letters, telegrams, or other forms of correspondence exchanged between Tesla and his contemporaries, shedding light on his collaborations, conflicts, and personal relationships. In addition to these specific collections, there are broader topics within the history of electrical engineering that are worth exploring. Firstly, the War of the Currents, which includes documents, articles, or research papers that explore the historical rivalry between Thomas Edison's direct current system and Tesla's alternating current system during the War of the Currents in the late 19th century. Secondly, the origins of electrical engineering, which includes articles or presentations that trace the development of electrical engineering as a discipline, highlighting key individuals such as Benjamin Franklin, Alessandro Volta, and André Marie Ampère. Thirdly, the IEEE role in shaping electrical engineering history, which includes documents or presentations that examine the IEEE role in advancing electrical engineering through conferences, publications, and standards development over the years. When examining documents related to NEC, it is important to consider the context of the company's evolution within the broader landscape of the electronics and telecommunications industries. This includes analyzing their technological innovations in areas such as semiconductors, communications equipment, and computer systems. Also consider their global expansion strategies and their impact on the development of technology standards. With Tesla, focusing on his contributions to alternating current power systems is essential. This includes studying his patents, technical papers, and demonstrations of AC technology, as well as examining his vision for wireless power transmission and its potential applications. When considering the War of the Currents, it is vital to analyze the technical and economic factors that contributed to the eventual dominance of alternating current systems. This includes assessing the advantages and disadvantages of both AC and DC systems, as well as evaluating the role of key figures such as Tesla, Edison, and George Westinghouse in shaping the outcome of this historical rivalry. When exploring the origins of electrical engineering, it is essential to understand the fundamental principles of electricity and magnetism, as well as the key experiments and discoveries that laid the foundation for the field. This includes studying the work of early pioneers such as Benjamin Franklin, Alessandro Volta, André Marie Ampère, George Ohm, and Michael Faraday. In the context of the IEEE role in shaping electrical engineering history, it is important to analyze the organization's contributions to the development of industry standards, the dissemination of technical knowledge through publications and conferences, and the promotion of innovation and collaboration among engineers and researchers. Grounding histories are also an important subject to study. Grounding in electrical engineering refers to creating an intentional low-resistance path to the earth. This path allows for the safe dissipation of fault currents, protecting equipment and personnel from electrical shock. The history of grounding practices is intertwined with the development of electrical safety standards and the understanding of electrical phenomena. Early electrical systems often lacked effective grounding, leading to numerous accidents and fires. Over time, engineers recognized the importance of grounding for preventing electrical hazards. The development of grounding techniques and equipment has been a continuous process, driven by advancements in technology and a growing awareness of electrical safety. Key milestones in grounding history include the introduction of grounded neutral systems, the development of ground fault circuit interrupters, and the establishment of grounding standards by organizations such as the IEEE and the National Fire Protection Association known as NFPA. The NEC, which is the National Electrical Code, plays a crucial role in specifying grounding requirements for electrical installations. NEC histories are closely related to grounding. The NEC is a set of standards developed in the United States for the safe installation of electrical wiring and equipment. It is updated every 3 years by the NFPA. The NEC covers a wide range of electrical topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is not law itself, but it is widely adopted by state and local jurisdictions, making it a legal requirement in many areas. The history of the NEC reflects the evolution of electrical technology and safety practices. The first edition of the NEC was published in 1897, and it has been revised and updated numerous times since then to keep pace with advancements in electrical engineering. Key changes in the NEC over the years have included the introduction of new wiring methods, the expansion of grounding requirements, and the adoption of new safety technologies. Each edition of the NEC incorporates revisions and additions based on proposals submitted by industry experts, engineers, and other stakeholders. The NEC is an essential resource for electrical contractors, engineers, inspectors, and anyone involved in the design, installation, or maintenance of electrical systems. When researching grounding histories, it's beneficial to focus on specific aspects or eras. One area of focus could be the early days of electrical power distribution. This would involve researching the challenges faced in providing safe and reliable electrical power in the late 19th and early 20th centuries. Key figures and companies involved in the development of grounding systems during this period could be studied. This research could involve analyzing early electrical codes, patents, and technical publications. Another area of focus could be the development of ground fault circuit interrupters called GFCIs. GFCIs are devices that detect ground faults and quickly interrupt the flow of electricity, preventing electrical shock. Researching the history of GFCIs would involve examining the technical challenges in developing these devices, the regulatory requirements for their use, and their impact on electrical safety. This research could involve analyzing patents, technical papers, and accident reports. Another area of focus could be the evolution of grounding requirements in the NEC. The NEC has played a crucial role in shaping grounding practices in the United States. Researching the history of grounding requirements in the NEC would involve examining changes in the code over time, the rationale behind these changes, and their impact on electrical safety. This research could involve analyzing past editions of the NEC committee reports and public comments. It is also important to consider the different types of grounding systems used in various applications. These include equipment grounding, system grounding, and grounding for sensitive electronic equipment. Each type of grounding system has its own specific requirements and challenges. Researching these different grounding systems would involve examining the technical standards, best practices, and case studies associated with each type. Also, international grounding standards can provide a broader perspective on grounding practices. Comparing grounding standards from different countries can reveal different approaches to electrical safety and the rationale behind these differences. This research could involve analyzing international electrical codes, technical publications, and case studies. The NEC contains numerous articles related to grounding and bonding, each addressing specific aspects of electrical system safety. Article 250 provides the general requirements for grounding and bonding. It covers topics such as grounding electrode systems, equipment grounding conductors, and bonding of metal parts. Article 250.4 addresses general requirements for grounding and bonding, emphasizing the need to create a low impedance path for fault current to facilitate the operation of overcurrent devices. It outlines the requirements for both grounded and ungrounded systems. Article 250.8 specifies methods of grounding and bonding connections, detailing acceptable ways to connect grounding and bonding conductors to equipment and grounding electrodes. It covers topics such as the use of listed connectors, exothermic welding, and other approved methods. Article 250.20 covers systems to be grounded, specifying which electrical systems must be grounded for safety. This includes systems operating at certain voltages and configurations, such as alternating current systems with a neutral conductor. Article 250.24 addresses grounding service supplied alternating current systems, detailing the requirements for grounding the neutral conductor of service-supplied AC systems. It covers topics such as the size of the grounding electrode conductor and the location of the grounding connection. Article 250.28 specifies the bonding jumper, detailing the requirements for the bonding jumper that connects the equipment grounding conductor to the grounded conductor at the service. It covers topics such as the size and material of the bonding jumper. Article 250.30 covers grounding separately derived alternating current systems, detailing the requirements for grounding separately derived AC systems such as those supplied by generators or transformers. It covers topics such as the location of the grounding connection and the size of the grounding electrode conductor. Article 250.50 addresses grounding electrode system, detailing the requirements for the grounding electrode system, which consists of the grounding electrodes and the grounding electrode conductor. It covers topics such as the types of grounding electrodes that are permitted and the requirements for their installation. Article 250.52 specifies grounding electrodes, detailing the types of grounding electrodes that are permitted, such as metal underground water pipes, metal frames of buildings, and ground rods. It covers topics such as the size and installation requirements for each type of grounding electrode. Article 250.64 covers grounding electrode conductor installation, detailing the requirements for the installation of the grounding electrode conductor, which connects the grounding electrode to the electrical system. It covers topics such as the routing and protection of the grounding electrode conductor. Article 250.66 specifies the size of the grounding electrode conductor, detailing the requirements for the size of the grounding electrode conductor based on the size of the service entrance conductors. It provides tables and calculations for determining the appropriate size of the grounding electrode conductor. Article 250.92 addresses services equipment enclosures, raceways, cable trays, and cable bus, specifying the bonding requirements for service equipment enclosures, raceways, cable trays, and cable bus. It covers topics such as the use of bonding jumpers and the methods of bonding these metal parts. Article 250.94 covers methods of equipment grounding, specifying the methods of equipment grounding, which is the connection of non-current carrying metal parts of equipment to the grounding system. It covers topics such as the use of equipment grounding conductors and the types of equipment that must be grounded. Article 250.102 specifies bonding jumpers and system bonding jumpers, detailing the requirements for bonding jumpers and system bonding jumpers, which are used to connect different parts of the grounding system together. It covers topics such as the size and material of the bonding jumpers. Article 250.104 addresses bonding of piping systems and exposed structural metal, specifying the bonding requirements for metal water piping systems, metal gas piping systems, and exposed structural metal. It covers topics such as the size and location of the bonding connections. Article 250.118 specifies types of equipment grounding conductors, detailing the types of equipment grounding conductors that are permitted, such as copper conductors, aluminum conductors, and rigid metal conduit. It covers topics such as the ampacity and installation requirements for each type of equipment grounding conductor. Article 250.122 covers size of equipment grounding conductors, detailing the requirements for the size of equipment grounding conductors based on the size of the overcurrent protective device. It provides tables and calculations for determining the appropriate size of the equipment grounding conductor. Article 250.130 addresses equipment grounding conductor connections, specifying the requirements for connecting equipment grounding conductors to equipment and to the grounding system. It covers topics such as the use of listed connectors and the methods of making secure connections. Article 250.134 covers equipment fastened to metal surfaces, specifying the grounding requirements for equipment that is fastened to metal surfaces, such as metal enclosures or metal panels. It covers topics such as the use of bonding jumpers and the methods of ensuring a good ground connection. Article 250.146 addresses connecting receptacle grounding terminal to box, specifying the requirements for connecting the grounding terminal of a receptacle to a metal outlet box. It covers topics such as the use of self-grounding receptacles and the methods of bonding the receptacle to the box. In addition to Article 250, other articles in the NEC also address grounding and bonding requirements for specific types of equipment and installations. Article 406.4 addresses receptacles, cord connectors, and attachment plugs, otherwise known as attachment caps, specifying the grounding requirements for receptacles, cord connectors, and attachment plugs. It covers topics such as the use of grounding type receptacles and the requirements for grounding portable equipment. Article 408.41 addresses ground fault protection for equipment, specifying the requirements for ground fault protection of equipment, which is intended to protect equipment from damage due to ground faults. It covers topics such as the types of equipment that require ground fault protection and the performance requirements for ground fault protective devices. Article 430 addresses motors, motor circuits, and controllers, specifying the grounding requirements for motors, motor circuits, and motor controllers. It covers topics such as the use of equipment grounding conductors and the methods of grounding motor frames. Article 440 addresses air conditioning and refrigerating equipment, specifying the grounding requirements for air conditioning and refrigerating equipment. It covers topics such as the use of equipment grounding conductors and the methods of grounding equipment enclosures. Article 450 addresses transformers, specifying the grounding requirements for transformers. It covers topics such as the grounding of transformer enclosures and the grounding of transformer secondary windings. Article 500 through Article 516 address hazardous classified locations, specifying the grounding requirements for electrical equipment installed in hazardous classified locations such as areas where flammable gases or vapors are present. It covers topics such as the use of intrinsically safe equipment and the methods of grounding equipment in hazardous locations. These articles, along with Article 250, provide a comprehensive set of requirements for grounding and bonding electrical systems, ensuring the safety of people and property. In researching NEC histories, it's essential to understand how these articles have evolved over time and the rationale behind the changes. Consider the specific application or type of electrical system being studied and focus on the relevant articles in the NEC. Tesla's work on alternating current systems revolutionized electrical power distribution. His inventions, such as the AC induction motor and the polyphase power system, made it possible to transmit electricity over long distances with minimal losses. Tesla's contributions were crucial in the war of the current, where alternating current eventually prevailed over Thomas Edison's direct current system. Tesla's work extended beyond AC power systems. He also explored high-frequency currents, wireless communication, and various other areas of electrical engineering. His research laid the foundation for many technologies that are still used today. Tesla's inventions and ideas were often ahead of their time, and he faced numerous challenges in bringing them to fruition. He was a visionary inventor who made a lasting impact in the world. When researching Tesla's work, it's important to delve into his original papers, patents, and laboratory notebooks. These documents provide valuable insights into his thinking and his experimental methods. Also, study the historical context in which Tesla worked, including the scientific and technological developments of his time. Understanding the challenges and opportunities that Tesla faced can provide a deeper appreciation of his achievements. Consider the impact of Tesla's work on society and technology. His inventions have transformed the way we live and work, and his legacy continues to inspire engineers and inventors today.